Hey everyone, it's pretty wild to think that a simple coil of wire can actually resist the flow of electricity, even if there's nothing physically blocking it.
It's true. And it's all thanks to this invisible force.
Which we call
Inductance.
Yeah, inductance. And
We're diving into that today.
we're going to be looking at this super interesting phenomenon where magnetic fields basically push back against changes in electric current.
It's like they don't want the current to change
Right.
at all.
Well, we're your AI experts.
That's right.
And we're here to break all of this down for you.
Absolutely.
So let's just start with the basics here.
Okay.
What exactly is inductance?
Well, inductance is kind of like a built-in resistance to change in an electrical conductor. It doesn't want that flow of current to change at all.
Whether it's increasing or decreasing?
Exactly. Increasing or decreasing.
So it's almost like an electrical inertia.
That's a great way to think about it.
Yeah.
But what's really fascinating is this resistance isn't from something physically blocking the current.
It all comes down to the magnetic field that forms around the conductor.
Yeah, because when electricity flows through a wire, it creates a magnetic field around it, just like Ampere's law states. The stronger the current, the stronger that magnetic field.
Exactly. That's exactly right.
But things get really interesting when that current starts to change.
That's when the fun begins.
What happens then?
Well, when the current changes, the magnetic field around that conductor, it changes too.
Yeah.
And that shifting magnetic field, it actually induces an electromotive force,
Okay.
or EMF,
Uh-huh.
you might notice voltage, back into the conductor.
So the conductor is creating its own opposition to the change.
It's basically a self-imposed resistance to change.
Wow.
And this induced voltage always acts to oppose the change in current. It's Lenz's law, always pushing back.
Okay, so the changing current creates a changing magnetic field,
Right.
which then creates a voltage
Yes.
that tries to stop the current from changing in the first place.
It's like a chain reaction.
A chain reaction of push and pull, that's inductance for you.
So is there a unit of measurement for this? For inductance?
Yes, we measure it in henries, H for short,
Okay.
named after Joseph Henry, a brilliant physicist.
Okay.
1 Henry means 1 volt is induced when the current changes at a rate of 1 ampere per second.
So even this invisible force has its own unit of measurement.
It does. It's amazing how we can quantify these things, isn't it?
It really is. Science is so cool.
It is.
But I'm guessing inductance isn't always the same, right?
You're right, it can vary.
What are some of the things that affect it?
Well, one of the biggest factors is the shape of the conductor.
Okay.
So, for example, a coiled wire has a much higher inductance than a straight wire of the same length.
Why is that?
It's all about those magnetic field lines.
Okay.
They can actually loop through the coil multiple times, increasing the overall magnetic flux.
So the shape matters.
Shape definitely matters.
I lost.
The type of material that's near the conductor,
That also plays a big role. So materials that are good at supporting magnetic fields, like iron, they can really boost the inductance. They make the magnetic field stronger, which means a stronger pushback against those current changes.
so a coil of wire near a piece of iron would have a higher inductance than the same coil without the iron.
Exactly, you got it. And then there's one more crucial factor: the number of turns in a coil. More turns, higher inductance.
So the more turns you have in a coil, the higher the inductance.
That's right. And in fact, inductance is actually proportional to the square of the number of turns.
So if you double the number of turns, you quadruple the inductance.
Exactly. It's a powerful relationship.
Yeah,
And it's fundamental to how we design and use inductors in circuits.
it's amazing how much is going on even in a simple coil of wire.
It really is, and we've only just begun to explore it.
That's true because we've only talked about what happens in a single coil so far.
Exactly, just self-inductance. But what happens when we bring multiple coils into the picture?
Well, that's when things get even more interesting.
I bet. I can't wait to find out more.
Well, we'll dive into all of that in the next part of our video.
Okay.
We're going to be exploring the concept of mutual inductance
Okay.
and how it plays a key role in technologies like transformers.
Ooh, transformers. Those are essential.
Absolutely essential.
I can't wait to learn more about that.
Well, stay tuned for the next part of our series.
All right, we'll see you then. So last time, we were talking all about self-inductance.
Right.
How a single coil of wire creates this invisible force field
Yeah.
that resists any changes in the current.
It really is fascinating, isn't it?
It is. And we even talked about all those factors that can affect it,
Yeah.
like the shape of the coil, the material nearby,
Right.
and even the number of turns.
Absolutely. All of those things play a role.
It's crazy how much is going on even in a simple coil of wire.
It really is, but it doesn't stop there.
It doesn't.
No, things get even more interesting when we bring in alternating current, or AC.
Oh, AC, that's what we use in our homes, right?
Exactly. The current that's always switching direction.
Yeah, constantly going back and forth.
Like a wave.
So what happens when AC meets an inductor?
It gets interesting, that's for sure.
Does the inductor still resist those changes in current,
Oh, absolutely. It doesn't discriminate.
even though they're happening constantly?
All the time. Remember, inductance is all about opposing any change in current,
Okay.
whether it's increasing, decreasing, or switching directions.
So the inductor's always pushing back against that AC current.
Always. Yeah, it's like a constant tug of war.
So does that mean the induced voltage is also AC?
It does. You're absolutely right. The
Mhm.
induced voltage mirrors the current, but there's a twist.
A twist. What is it?
They're not exactly in sync. We say they're out of phase.
Out of phase.
Yeah, think of it like two waves, one for the voltage and one for the current.
Okay.
In an inductor, the voltage wave hits its peak before the current wave.
So it's like the voltage wave is leading the way.
Exactly. And the current wave's trying to catch up.
So they're not perfectly aligned.
Nope, they're a quarter of a cycle apart, or 90 degrees out of phase.
Okay.
And this phase difference, it's really important for understanding how inductors work with AC circuits, because it leads to something called inductive reactance.
Okay, inductive reactance.
Yeah, it sounds a bit intimidating,
Yeah, a little
but it's
bit.
not too bad. Think of it like the inductor's resistance to AC.
So like how a resistor resists the flow of both AC and DC,
Exactly.
an inductor has its own way of opposing AC.
Precisely, but it's special.
What makes it so special?
Well, inductive reactance, it actually depends on the frequency of the AC signal.
Oh, the frequency, you mean how quickly the current is switching directions?
Exactly. The higher the frequency, the stronger the opposition from the inductor.
Because higher frequency means more rapid changes in current.
Right, and remember, the inductor's whole deal is fighting against change.
Yeah, so if the current's flipping directions really fast, the
Yeah.
inductor's basically like, whoa, slow down there, buddy.
Haha, exactly. It pushes back harder against those quick changes.
So inductive reactance increases with frequency.
That's right. Higher frequency, more resistance.
Okay, that makes sense. So inductive reactance is all about how much an inductor resists AC.
Exactly.
And the faster the AC changes, the more it resists.
You got it. It's a dynamic relationship.
So we've been talking about self-inductance.
Yeah.
What happens in a single coil,
Right.
but what happens when we have more than one coil?
Ah, that's where we get into mutual inductance.
Mutual inductance. So one coil's magnetic field can affect another coil.
You got it. It's like they're having an electromagnetic conversation.
Sounds like electromagnetic interference.
It is similar, but it can be incredibly useful.
Okay.
Like in transformers.
Transformers.
Yeah, those devices that let us step up or step down voltages, they rely entirely on mutual inductance.
Wow. Those are essential for our power grid.
Right, absolutely essential. Can't imagine our power system without them.
I can't imagine transmitting electricity over long distances without transformers.
It would be a nightmare. They allow us to control and distribute energy so effectively.
So this electromagnetic conversation between coils is happening all around us,
It is. It's happening all the time.
enabling all sorts of technologies.
Yeah, from power grids to wireless charging to radio communication.
It's incredible how much this invisible force shapes our modern world.
It really is, and we're only just beginning to understand its full potential.
So we've explored a lot about inductance,
We have
from the basis
all the way to transformers.
and how multiple coils can interact.
Mutual inductance, right.
Yeah, and how inductors can store energy in their magnetic fields.
Just like tiny electromagnetic batteries.
It's pretty amazing to think about how this seemingly simple concept plays such a huge role.
It really is. It's everywhere.
What other applications should our viewers know about?
Oh, tons. We've talked about transformers for the power grid, but inductance is also crucial for electric motors.
Electric motors.
Yeah, the things that convert electrical energy into mechanical energy.
Oh, right.
Without inductance, we wouldn't have the motors that power everything from our cars.
To our appliances.
Exactly. So inductance is literally a driving force behind our modern world.
It really is. And what about things like radio technology?
Oh, absolutely. Antennas use inductance to transmit and receive radio waves.
Really?
Yeah, every time we listen to the radio or stream music online.
We have inductance to thank.
Exactly. It's not just about power grids and motors.
It's about communication and entertainment.
And it is. It's connecting us in ways we don't even realize.
It's incredible.
And don't forget wireless power transfer.
Oh,
Charging our phones without plugging them in.
that's a game changer for sure.
It is. Inductance makes it all possible.
So inductance is shaping the future of technology in a big way.
It really is. As we keep innovating, understanding and harnessing inductance is going to be key.
Well, we've learned so much about inductance.
Everything from basic definitions to real-world applications.
It's been an electrifying journey.
It has. I'm glad we could take it together.
Me too. But before we wrap up, is there anything you'd like to leave our viewers with?
Definitely. If inductance can be used for wireless power transfer, what other potential applications can you imagine?
Ooh, that's a great question.
What else could we use this powerful force for?
Share your ideas in the comments below. We'd love to hear your thoughts. And if you enjoyed this video, don't forget to subscribe to our channel,
Yeah, we've got lots more exciting topics coming up.
including our next video all about electric power.
Until then, keep those currents flowing.
And stay curious.